Alright, so in one of my early videos back in June, I 3D printed these radical flat wave cams for my handboard trucks that had absolutely no resistance. And that was kind of a quick, fun video, but it was part of a larger project that I was meaning to get into, but my camera broke. So I'm trying to work my way back into it right now, so I'm a little rusty on all the details of what I figured out. But I wanted to talk about the way that these wave cams work and how we can optimize them for better performance. So this is a wave cam where I've painted half of it black. And if you look back at our old original trucks video, where we first talked about wave cams, we talk about how it has this parabolic curve to it. And we were actually under the impression at that time that because it had a parabolic curve, that the response was following this parabolic arc. See, I was imagining that, you know, it would sit resting at the center and it would climb this arc, and the further it climbed, the steeper the slope, and so the sharper or more progressive the spring response was. But looking at these in more detail, I realized that that was wrong. That's completely wrong. Alright, so I'm going to try to show you how this works. So first off, just the real basics. These two cams are inside the truck, and as you twist, the length of these two cams gets longer. So if I go like this and go all the way, it gets a lot taller, and then it collapses down again. And that is an action that compresses a spring. So if you look when it's flat, it's in contact everywhere around the surface of the cam. So that's good. That means that there's weight everywhere and it's distributing the load, and that's what you want. You want interaction as much places as possible. But as I twist it, get real close, you'll see if the instant I move it, the only place it's actually contacting is right here, and on the opposite side right there. And if I twist it in the opposite direction, there's a big gap here, and now on this side it's contacting there and there. So as a matter of fact, the actual only functional contact points on this right cam for the amount of rotation it actually gets in use is only between these two black lines. So that means that the whole rest of the cam, in terms of, you know, its surface area and its slope, is completely unused. So while I was thinking that, oh, because it's got a low slope here and a higher slope here, and, you know, it creates like a parabola, I was thinking, you know, over here it's going to be a lower angle, and down here it's going to be a higher angle. But that doesn't work, because the only part and the only angle it uses is from here to there, which, as it turns out, is about a 45-degree angle. So what I've done here is I've made a little gauge. So on this side it's got tick marks every 5 degrees, and it acts like a little protractor, and I can turn the cam and mark and read what degree of turning it is at. And on the other side, I've got these other marks, and there's a black or white mark for every millimeter. So this whole stack is 1 centimeter tall. There's 5 white lines and 5 black lines. And I can turn this, and I can count and look, and also measure with my calipers what the relationship is between the number of degrees it's been turned and the height that it raises up. So if I take a look at this and I just turn it to 10 degrees, let's see, 5, 10, right there. It works out so that it's about works out to be about a centimeter per 10 degrees. And I've tested this on this one, and I've also gone and I've tested it on this cam. So this cam is just got 45-degree wedges on it. So if this cam is the same this way as it is this way, then that means that these angles are symmetric and flippable, so this angle has to be 45 degrees. And because the only contact point in use is only that wide, even though that isn't a perfect 45-degree line, it's really, really close to, because it's not flat, but it's really close. So I can approximate it really, really accurately, just making a cam that just looks like that. So I've measured both these cams, and there's my little graph there. I only have enough. I can only measure like about 3 points accurately. I can't go and measure 1 degree and 2, or 5, 10, 15, 20. I'm only able to do about every 10 degrees. But they look to be equivalent to each other. So that means that this cam just isn't doing what I was hoping it would. So that leads us to the first stage of this project. So if we look back at this cam here, pop this out, what I've done is I've gone and I've measured the degree of turning that the hanger does when I'm writing and where it stops at. And then I used this device and a couple other things to figure out how far this cam rotates when you actually are using it. And that's kind of where I came up with the width of these black lines, right? So what I determined was that because we were only using this much and that much and that much and that much, that's less space than this width and that width and that width and that width. So I hypothesized that instead of splitting the cam into 2 halves, let's take a look at this cam. This is better for the camera. So it's just, instead of just doing it in 2 halves, what I could do is I could split this 45 design, and that's in there. There. I could split this 45 design into thirds. Where is it? That's not that one. There it is. Thirds. Do I have a black one? I've got a black one. So I was able to split the design into thirds. So there's enough room on the cam to, instead of making it halves, to do thirds. So this cam should function. So this one's got rounds on it. So this cam should function exactly the same way that this cam functions. But there's one huge advantage already. So we haven't changed the mechanics of it yet at all. I haven't changed, so I could make it so that, so I've got on this graph, that I've made of the characteristics of the cam. So it's this relationship is still a straight line like that. And I could do something where it's more like an S and then more different S. And I could make it so it's a relationship that's more like an S, which is what I wanted initially. Which is what how I thought it worked initially, because it kind of has this parabolic shape. So I could do something like that, but so far we haven't done that. All we've done is we split it into thirds instead of in halves. So the big advantage with that is because this cam, this one's a better example. This cam has a lot of material in this dimension and not a lot in this dimension. And basically the cams have a liability to snap. But by breaking it into thirds, we are now using, it's not symmetric anymore. So it doesn't have, there. So yeah, so this line is perpendicular to that line, that groove, and there's no weak planes. This cam, performing the exact same way. Where did I have to go? Is this guy? As this one should be a lot less liable to snap. So that already is one big improvement. There is a problem though, in the fact that this still won't really work very well, because I've got a big lobe on this side and a small lobe on this side, and so these lobes are relatively weak compared to these lobes. And so, anyway, so the problem with this one is it just digs in and grabs. It's not a very smooth shape. So I need to refine the shape a bit more. But also there is another problem that I need help solving this. I don't know how to do this. So there is one difference between. Well, I lied a little bit when I said these were equivalent, because there's a problem. And that is that this 45 is just a line cut straight across, right? What it needs to be is it needs to be projected from center. So let me draw the color this real fast. Okay, so this should be easier to see. So whereas this cam has just got a straight line cut across it, this one is projected around the center, so that at any one point along this surface, it's level here, 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 and that allows it to be really smooth in its action and to have a contact point that is a straight line across all these places. Now, this is a great way to approximate it without weight on it, and it's kind of close. But you put weight on it and it doesn't work, because it's, instead of loading up on a line across, it's loading up on this tiny point here and on this tiny point here, and the cams, they buckle at the edges, and then they mushroom out and it jams. It doesn't work. So what I need to figure out before I can take this a step further is how to model something like this in Fusion 360 instead of something like this. And then I've got to do it into a 3-leaf clover design, and then I got to figure a way to make it so it's acting like a cam, so that it's following an arc instead of a straight line. Because if I have it following an arc, I can make it so that at the center it's really loose and it has a progressive resistance. Or I can make it so that it has a little bit of diminishing return if I want to be a little tippy. I think the best solution is to have it be a little bit progressive. Not very progressive, but just a little bit. So it's stiff as you need it to be at center. But then as you get out of it, it increases. And so that you can feel, you can gauge how far you're leaning by how much force you're putting into the deck. So anyway, that is my dilemma, and hopefully I'm able to get some help and some resources, probably from this video, on how to solve this modeling problem. So there we go. I've been doing a lot of other stuff with 3D printing. I might as well do a little bit of an update here. I'm working on 3D printing some Roja hangers that I think I can do inline axis, or inline axles. So I'll have zero rake Roja hangers is the thing I'm doing. I've been working with one of the engineers from Other Planet, and he's been 3D printing some new truck designs that he's been messing with, and I've been printing them up for him. And I've been working on my own design of a 3D printed truck, which I can't show. Here is the board that my 3D printed truck goes on, though. It's all nice, and it's just ABS decorative plastic. Come on. Oops. There we go. So it's just decorative ABS plastic, but I wanted something, because I take the trucks on and off these all the time, I didn't want to be tearing up my workspace. So I've also got this voxel footstop, which is pretty cool. And then I was able to get the model for it, and this is the one I printed, which is nice. I use a lot bigger nozzle. I'm having huge, giant layer lines. Yeah, so having big, visible layer lines is kind of really grown on me. So anyway, so I have been doing a lot of 3D printing in the background. I've given up on my 3D printed bearing cleaner until it's warm out again. But I've gotten a lot more skilled at modeling, and we'll see how it goes. So I also have this 3D printed bushing, which won't really work very well for a regular bushing, but I've got a project for these where I just needed some cheap bushings, and having a 3D printer is really nice. This is flexible filament, but it's like 95A, which is a lot harder than you want as a bushing. So it's actually, if you can make out the color, the base is completely solid, and then the rest of it is kind of got a hollow fill to it. So it's kind of like a dual durometer bushing, but instead of changing the material, I've just changed the density of this harder material. So this bottom sits really nicely into a bushing seat and won't move around because it's got a ton of lateral support. So it can't compress side to side in the seat, and but it can comply and move up here, which is exactly what I needed for my application. But it has no rebound because this is not an elastic. It's flexible, but it's not elastic. So in a conventional truck, these would be terrible bushings, but I'm definitely going to try it anyway. So there is the post-video update, and hopefully I'll get more videos out now that my camera is working. I've really gotten out of the habit of making videos. But anyway, I'm rambling on now. Longboard technology, over and out.